Hello, AP Stat students. Today we're continuing our discussion of random variables, and we'll be talking about transforming random variables today. And recall, back in Unit 1, we learned about linear transformations of quantitative variables. And we learned what happens when you multiply every number in a set of data by a certain value, and we learned what happens when you add or subtract a certain value from an entire set of data. So let's review that concept real quickly here. So let's say we had a set of data where the mean was 50 and the standard deviation was 15. If we multiplied all the data by 3, what effect does this have on the mean and standard deviation? So it'd be basically taking 3x, or 3 times the mean of x. So it'd be 50 times 3. So the new mean would be 150. And then for the standard deviation, the same thing is true. We'd multiply that by 3, and we would get 45. Okay? So when we multiply, remember, it changes everything. It changes the mean, it changes the standard deviation, it changes quartiles, it changes range. Multiplication changes every single value. Okay? Also, if we add 10 to every piece of data, what effect does that have on the mean and standard deviation? Well, adding only changes things that measure position, so like mean, median, quartiles, things like that. And it makes them all 10 units higher. So in this case, the mean would change from 50 to 60. But the standard deviation of x plus 10 would still be 15. Okay? Adding a constant to a set of data does not change how spread out that data is. So that plus 10 only affects measures of position. So things like range, IQR, standard deviation, those type of things, interquartile range, those would not change simply by adding 10 to every piece of data. It's only multiplying that changes the measures of spread. So how does this relate to random variables? It's almost exactly the same. Okay, so just to reiterate, when you multiply a set of data by a constant, it changes all of the measurements, whether they're measures of center, position, or spread. When we add a constant to a set of data, it only changes measures of center and position. It does not affect spread measurements. So random variables are affected in the same way as quantitative data. Okay? So suppose we're performing a linear transformation, bx plus a on a random variable x, which means we're multiplying every piece of data by b and we're adding a. Well, for the mean, we would do both. We would multiply the mean by b, and we'd add a to the mean as well. Okay, so for the mean, it gets affected by both numbers. For the standard deviation, it only gets affected by what we're multiplying by. So it does not matter that we're adding a to every piece of data. The only thing it matters, or the only thing the standard deviation cares about, is what we're multiplying by. And then this third equation over here, if you had the variance that we're talking about instead of the standard deviation, and you wanted to multiply the variance by that b, you'd actually have to multiply the variance by b squared. Okay, think of variance land as kind of its own little place where everything there is squared. Okay, standard deviation is squared. That's what makes variance. And if I want to multiply the variance by a number, it has to be a number that was squared. So here's an example. Example 1: exercise. Creative name, spends a lot of time in a health facility and likes to work out on an elliptical trainer. The time he daily spends on the trainer is different depending on how much of a hurry he's in. The table below shows the probability distribution of his exercise times. Let x represent the amount of time spent on the elliptical trainer. Okay, so you can see there's a 10% chance he spends 15 minutes. The most likely thing that happens is that he has 45 minutes to spend. That happens 40% of the time. And then there's a very small chance he exercises more than 45 minutes. So first two questions are find the mean and standard deviation of x. And this is where you use your calculator and enter your data and then do one variable stats on L1 and L2. This is back to just the mean of a random variable. So the mean amount of time he spends on the machine is 39 minutes. And then the standard deviation, I get that in the same place. On my calculator is 11.4 minutes. Okay. So now, obviously, he never actually spends 39 minutes on the machine. But if you kept track of him for like 6 months of him going to the workout like 5 times a week, and you timed him on the elliptical trainer, he should average 39 minutes. Okay, and then with a spread of about 11.4 minutes on either side of that would be his usual amount of exercise. Now, here's where the linear transformation comes in. So assume that each minute on the elliptical burns 18 calories. Also assume that after he trains on the elliptical, he then lifts weights, which burns an additional 250 calories. Okay, so I want to find the mean of the daily calories burned. So this is a linear transformation. He's going to burn 18 calories times how many minutes he rides the elliptical, so it's 18 per minute. And then he's also going to burn 250 calories by lifting weights later. So the mean of the daily calories burned would be 18 times 39 plus the 250. Remember, for means, adding and multiplying both affect them. So I have to do both. So I do 18 times 39, which is 702, and then add the 250, which is 952. Okay, so that would be his average amount of calories burned based on the probability distribution. Now, for the standard deviation of the calories burned, all we really care about for the standard deviation is that it's 18 times how many minutes we rode. We don't care about the adding 250. The 250 is a constant and does not change the spread. So our standard deviation before was 11.4, so I'm going to multiply 18 by 11.4, and it's 205.2. Okay, so the multiplying by 18 and the adding 250, they both affect the mean. So I take the mean 39 and multiply it by 18 and add the 250. But for the standard deviation, all I care about is the multiplying by 18. So I take the old standard deviation times 18. Okay, so hopefully this is sounding familiar to you. It's kind of a review of the stuff we did in Unit 1, where we did linear transformations of quantitative data. Here's one more example. Example 2. It says the probability that a customer selects 1, 2, 3, 4, or 5 items at a convenience store is as follows. Okay, so it looks like the most frequently event that happens is the customer selects one item. That happens 32% of the time. And it looks like the second most likely thing is that 3 items would be selected. And interesting, the least likely thing is 2 items. Which is a less chance of them picking 5. So very interesting. But we'd like to find the expected value in the standard deviation of the number of items purchased. So this would be on average, how many items does the customer purchase? And again, we go to our calculators and use enter x as in L1, p of x as in L2, and do one variable stats on L1 and L2. And we get that the mean amount of items purchased is 2.72. And the standard deviations of items purchased is 1.45. So on average, customers will buy 2.72 items with a standard deviation of 1.45 items in either direction. Okay. Now, let's do a transformation now of this random variable. So the average price of each item bought is $2. So it's $2 per item, and they can convince customers to donate $150 to charity most of the time, it looks like. So that's my linear transformation, 2 times x plus 150. So now I want to find this mean and standard deviation of how much a customer spends at the convenience store. So for the mean, we're going to do both, right? We're going to multiply by $2 per item, and then we're going to add the 150. Okay, for the standard deviation, all I care about is that we're multiplying by 2, so it's going to be 2 times 145. I do not care about adding the additional 150. That is not going to change the spread. So for the mean amount spent, we'd expect $6.94 to be spent per customer. And then for the standard deviation, I do 2 times 1.45, and I get $2.90. So most customers, on average, will spend $6.94 with a standard deviation of about $2.90 in either direction of that. And remember, there probably won't be a customer that actually spends $6.94. But if you kept track of hundreds of customers, thousands of customers at the convenience store, the customers should average $6.94. And it's important that you understand that interpretation of what the expected value means.